You're holding a massive 1,000-page antique book, and your job is to find one specific mention of the name John. But there is a catch. The book has no index at the back. You would have to start at page 1 and begin flipping, reading every single word to find what you need. Databases face this exact same problem. When you ask a database to find a specific piece of information, and it does not have an index to guide it, the computer is forced to check every single row of data, one by one. In the database world, this process is called a table scan. Here is a simple students table, with ID and name columns in no particular order. If we ask it to find John, it must slowly highlight the first row, then the second, moving down the list until it spots him. The solution to this search is a command called create index. It works exactly like the index at the back of a textbook. It tells the database to create a smart, organized shortcut directly to the data you want. This command helps us avoid those exhausting table scans by providing a direct path to the data we're looking for. Instead of making the computer sift through every single record from start to finish, we give it a map to find the right information much faster. Typing the create index command for the name column creates a separate, smaller reference column that lists names alphabetically. Now, searching for John skips scanning the whole table. It instantly jumps to the J section, following a direct arrow straight to John's exact row. Using create unique index on the student ID column gives the database a strict rule: actively block duplicates. If a duplicate ID is entered, the index flashes a lock icon and rejects it, keeping data clean. These commands solve our immediate problems with search speed and data errors. But to really master databases, we have to look under the hood and understand exactly how these indexes are physically stored on the hard drive. This brings us to the clustered index. Think of this like organizing a physical library bookshelf, where every book is lined up strictly by its spine number, from 1 to 100. Applying a clustered index to our student ID column visually shuffles and locks the entire row structure into ascending numerical order. Because physical rows can only have one specific physical order on the disk, a table can only ever have exactly one clustered index. But here is the problem. If our table is physically locked into numerical order by ID, how do we search for a student's name quickly without completely rearranging the physical table all over again? The answer is the non-clustered index. If the clustered index is the physical bookshelf, the non-clustered index is the library's card catalog. A non-clustered index builds a totally separate, alphabetized list. Direct arrows shoot from this list to the main table, acting as pointers to the exact physical row. Because they are separate, you can create multiple non-clustered indexes, like one for department, alongside name. This chart breaks down the two types. The clustered index physically reorders data, limiting you to one per table. The non-clustered index creates separate reference lists. You can have multiple, but they require extra memory to store. Building an efficient database means finding the right balance. You must weigh the fast, single physical order of a clustered index against the flexibility and extra memory cost of creating multiple non-clustered reference lists. The process of managing all these lists and pointers is called SQL performance tuning. It is a critical skill because if you write an inefficient query, the computer processor has to work extremely hard. A poorly optimized database can consume massive amounts of computing power, leaving server racks vibrating under the strain, sometimes crashing the entire system. Even with perfectly organized indexes, you still have to ask the database the right questions. We call these smart queries, and they often start with a simple rule about the asterisk symbol, which programmers use to select all. Using this symbol tells the database to grab every single column in a table, even the ones you don't need. Here we see why select all is a problem. Asking for every column creates a massive, heavy block of data that takes much more time to move through the system. If you only need the first and last names, ask for just those two slim columns. They glide through the system smoothly and save huge amounts of memory. The second rule of writing smart queries is knowing where to place your wildcards when searching text. A wildcard, usually represented by a %sign, is a placeholder you use when you only know part of a word. Look at our alphabetized index list. If you place a wildcard at the very beginning of your search term, the index gets lost. It doesn't know which letter to look for first, so the alphabetical order becomes useless. To keep your index working, you should always place your wildcards at the end of the search term, allowing the database to jump straight to the correct starting letter. Think of an index as your database's built-in navigation system. It maps out the fastest, most direct route to your data. But even the most brilliantly designed map will not help you if you write a query that refuses to follow the